Letter C is going to be Gibbs Free Energy. If you watch NCIS, I think it's a different Gibbs, but nevertheless, same last name. And Gibbs Free Energy is basically an energy that deals with any of the leftover energy from our delta H and delta S. So we might just define it as the energy, I was going to do capital E, the energy left over after bond breaking and bond forming and this energy is really our delta H, okay? So the energy left over after bond breaking and bond forming, and phase changes, if these have taken place, and these deal with our delta S. So whatever energy that's left over to do work, which kind of brings us right back to where we started. So energy left over to do work. Alright? And if you remember that kind of, in terms of, there's kind of energy we talked about in physics as well as in chemistry, and really energy is the ability to do work. Okay? So, if we have a couple examples, if we have water as a liquid going to water as a gas, okay? So we are just boiling water in a pot on the stove. A couple things are true. Our delta H is positive, alright? Delta H is positive, or we might say it's non-spontaneous. Okay? We're having to supply energy in order to boil water. At the same time, our delta S is positive as well, because disorder is increasing. Okay? But unfortunately, delta S being positive is a spontaneous reaction. Okay? If we look at water as a gas condensing into water as a liquid, in terms of bond breaking or bond forming, our delta H is a negative value, okay, which means it is exothermic, or we're losing energy to forming basically our intermolecular forces. So that is typically a spontaneous reaction, but our delta S is a negative value, which would indicate a non-spontaneous reaction. So, because these two things are competing against each other, there is something we have to take into consideration whenever we calculate Gibbs free energy. And really, temperature plays the ultimate deciding factor. So we might say just temperature is deciding factor for spontaneity. Alright, and we use this equation, which basically says delta G equals delta H minus T delta S. And T is in Kelvin, or it doesn't really equal kelvins, we're just going to say T in Kelvin temperature. Okay? In this case, we're going to say that delta G really tells us whether something is spontaneous or not. So if delta G equals a positive value, when does it equal a positive value? It equals a positive value if delta H is positive and delta S is negative. Okay? So if that's the case, we are really looking at not one of these examples. We're just going to say that every time that delta G is positive, our reaction is non-spontaneous. And every time that delta G is a negative value, it is always spontaneous. Alright, so if we had something that was exothermic, which is spontaneous, and then something that is becoming more disordered, this would be a positive value, and because we're subtracting a positive value, both our delta H would be negative and T delta S would be negative. Then delta G is negative. If we have something that was endothermic, that would be a positive delta H, and at the same time becoming more ordered, that would end up being a negative of a negative value becomes positive, so we're adding a positive to an already positive thing, and we have a positive delta G. And then lastly, delta G, if it equals 0, it tells us that we have an equilibrium state. Alright, and equilibrium is one of the big things we're going to talk about second semester. But know that if delta G equals 0, equilibrium is occurring, or it's in an equilibrium state. Alright, we're going to fill out this little table. You might just pause the podcast right here and just jot this table down in your notes, and we'll jump right into it. But we're just going to look at signs. So if delta H is a negative value, and then we're just going to do this negative, negative, positive, positive. Just going to put that in your notes. And then delta S, if we do positive first, then we're going to do negative, then we're going to do positive, and negative. Alright, so if delta H is negative and delta S is positive, and we have this equation to determine Gibbs free energy, delta G will always be negative. So we might just say it is spontaneous at all temperatures. Why can we say all temperatures? Because we're talking about Kelvin temperatures. Kelvins are always positive values. We can never have a negative Kelvin. So if our delta S is positive and T is positive, this will always be a negative value. If our delta H is negative and our delta S is negative, we could have both a negative delta G and we could have a positive delta G. Okay, so the negative would be spontaneous, while the positive is going to be non-spontaneous. And in this case, we might say it's spontaneous at low temperatures. But when is it non-spontaneous? If the temperature is high enough, it becomes non-spontaneous. So at high temperatures. Alright, if we have two positive values, so delta H is positive as well as delta S being positive, we can have both a negative delta G and we can have a positive delta G. So our negative delta G is going to be a spontaneous reaction, while our positive is going to be a non-spontaneous reaction again. And now, when is it going to be spontaneous? It's going to be spontaneous at high temperatures, because we need our negative T delta S to be a larger value than our delta H. And then when will it be non-spontaneous? At low temperatures. And then lastly, if our delta H is positive and our delta S is negative, if we put it into our Gibbs free energy equation, it will always be a positive value. Or we can say that it's going to be non-spontaneous at all temperatures. All this is algebra. If you want to memorize the table, you can. But know that delta G is really temperature dependent, and if our signs are the same, so in this instance, and in this instance, we really have to look at the temperature in order to determine spontaneity, whether it happens without external energy or whether it needs external energy to occur. Alright? The next thing is we're just going to take a single example and calculate it two different ways, both with our new equation and using just delta G values, which can be found in Appendix A as well. Alright? So it's going to be an example kind of with two parts. So our first line, so let's erase that actually. Okay. So our first example is going to be this equation. So example number 1, and we're going to do carbon monoxide gas plus 2 hydrogens, and they're going to be in the gas phase, are going to yield, let's see, what are they going to yield? They're going to yield methanol. And methanol is going to be at a gas as well. And all this is happening at 25 degrees Celsius. What is the 25 degrees Celsius good for? It is just it means the standard condition. So in our notes from last week, we have the little knot above really our H, and this is going to apply to our S, and it can apply to G as well. So just standard conditions would be 25 degrees Celsius, 1 mole of products or reactants, 1 molarity, and atmosphere we're going to assume is 1 atmosphere as well. Okay, so if we have this equation, and we looked at, we calculated our delta H. All right, so delta H, we're going to take our products minus our reactants. So if we look up methanol in the back of the book, we're going to find that it has a value of negative 201.2 kilojoules per mole. All right, and we're really going to multiply that by 1 because that's our coefficient front. And then we're going to subtract from that the sum of our reactants. So we have 1 carbon monoxide, and its value is negative 110.5 kilojoules per mole. And then we have 2 hydrogens, so plus 2 times. And hydrogen's value, because that's just hydrogen gas, that's the way it comes, it's in its most stable state, is going to be 0. And our answer to that is going to be, I'm just going to put it in a different color, we'll do green, is going to be negative 90.7 kilojoules per mole, if we only just leave it as per mole. The next thing we're going to calculate is going to be delta S. And again, we would look in the back of the book and find entropy values. If we look up methanol, there's one of them, and methanol's value is positive 238. And then here's the tricky part. It is not kilojoules, okay? But how is this measured? I let you know the other day. It is just measured in joules, okay? And this is a tricky place that the AP test will like to get you right here. And those last equation questions is knowing that you're going to have to divide your entropy values by 1,000. Okay? So we have products, and then we are going to subtract out reactants from our products. And in this case, carbon monoxide, we have one of them, and carbon monoxide's value is positive 197.6 joules per mole. All right? And we also have 2 moles of H, which is 130.6 joules per mole. And when we do this math, we get an answer of negative 221.7 joules per mole. I about did it. Joules per mole. Okay, so there is no kilojoule. Alright, so our next equation is we're just going to calculate delta G. And again, delta G equals delta H minus T delta S. And our delta H value was negative 90.7 kilojoules minus, what temperature is this all happening at? It's happening at 298 Kelvin. And we're going to multiply that by not negative 221.7, but negative 0.2217. And then these units now are kilojoules, and then it's per mole Kelvin, or there's going to be our Kelvin again, which we should have had up here. And then this answer, just as a final answer, is going to be negative 24.8 kilojoules per mole. Alright, and notice our Kelvin temperatures go away. Like this Kelvin right here is going to cancel with this Kelvin in the denominator. And our final answer is negative 24.8 kilojoules per mole. Example 2 is more kind of what you're going to be doing for most of your homework, I believe. I think you have one to do like that. But example 2 is simply our other way to calculate delta G. So delta G can also be calculated, this is going to be surprising, the sum of our products minus the sum of our reactants. And again, if you look in Appendix A at the back of the book, we have delta G values directly. So in this case, If we are calculating delta G, we're just going to have, again, our product was methanol. We had one of them, and its delta G value is negative 161.9. We're back to kilojoules per mole. And then we're going to subtract out the sum of our products. And carbon monoxide is negative 137, is negative 137.5 kilojoules, plus 2 times hydrogen, which is 0 again, kilojoules. And when we add all this up, we get a value of, hopefully something pretty close to this, and it is, we get a value of negative 24.7 kilojoules per mole. So hopefully, it doesn't matter which way we do it, we should get an answer that's pretty close and fairly constant. But there's kind of two ways to do this. If we don't have direct delta G values for our products and reactants, we can always look at their delta H and delta S's to cover this. And then if our temperature is not at 25 degrees, again, these delta G values are going to be delta G naught. And this is going to be products at 25 degrees and reactants at 25 degrees. So if the temperature is different than 25 degrees, or standard temperature, we would have to use the delta H minus T delta S equation. Alright, so two different ways to calculate delta G. Know that delta G is, again, just the leftover energy after bond breaking and bond forming, and as well as after phase changes that's available to do work.